Dana. So today I'm going to talk about near optimal averaging samplers and matrix samplers. This is a joint work with my advisor, David Zuckerman. So as you see, I put a nice picture of a person counting balls. So now we have a box containing red and blue balls, and how can we estimate the proportion of each color? And the naive answer would be just count all of them. But surely we want to do something smarter. We use the power of randomness and randomly sample some balls from the box. And just a few samples, we will get a very good estimation. So this problem can be formulated as follows. We have query access to an arbitrary unknown function f, which maps from 2 to the m to 0, 1. And we want to approximate the expectation of the f. So just you add all of the function values and divide it by 2 to the m. And then what we can do is pretty simple. We just draw uniform samples from this 2 to the m and calculate the average over these function values. And Chernoff bound guarantees us just by taking 1 over epsilon squared times log 1 over delta samples, then we have 1 minus delta confidence that your estimation would be epsilon close to the true expectation. And like as the motivation for all the de-randomization, true randomness is hard to get. And we want to say like, although 1 over epsilon squared times log 1 over delta uniform samples, like this is a small number of samples, but each sample costs us m random bits to sample from this 2 to the m domain. So so it's natural to ask, can we avoid using so much randomness? And to know that the full de-randomization will be impossible here because as you can imagine, if you just deterministically sample some points from this 2 to the m domain, and recall that we want to have a good estimation on every function. So then there were like 2 different functions we can never distinguish, and they can be totally different. So we have to query basically all the points for deterministic sampling. And so this leads to the definition of averaging samplers, where there is a function. You can think of this as an algorithm that takes in n random bits and it outputs t samples. And each sample is like a m Boolean string. And if you take the average over these samples, you have 1 minus delta confidence that you're epsilon close to the true expectation. And we study from 2 perspectives. And one is the randomness complexity, which is the n here, and the sample complexity t. And you can surely study from the computational complexity, and all the constructions we mentioned today all can run in polynomial type. So naturally, there's a trade-off between parameters. If you take full independence, you have perfect sample complexity, but you have a bad randomness complexity. If you run it deterministically, you don't have to pay any randomness, but you have terrible sample complexity. And there's a matching lower bound and almost matching lower bound and non-explicit construction that you basically need to pay m plus log 1 over delta random bits. So epsilon doesn't show up in the randomness bound. And for the sample complexity, it's 1 over epsilon squared times log 1 over delta, so which is the Chernoff bound. So the opt of the sample complexity is 1 over epsilon squared log 1 over delta. And the problem we want to study is that can we design an efficient averaging sampler that achieves this O of opt samples while only use O of m plus log 1 over delta random bits. And for this talk, we should think of this epsilon as 1 over poly m and delta being exponential of negative theta m. So then the randomness complexity we want to get will be O of m, and the sample complexity will be a poly m bound. Yeah, to warm up, like how do we usually say randomness? The easiest example would be just take pairwise independence. So instead of making like the distribution over all the samples being uniform, we want to say like if you look at 2, the marginal distribution on this 2 will be a uniform distribution. And this usually gives us a good concentration that by just using like Chebyshev's inequality, you can calculate it and show that by just taking 1 over delta epsilon square samples, this gives you a good delta epsilon sampler. And Chor and Goldreich proved that generating such a length t a pairwise independent sequence costs you m plus log t random bits. So this will give us very good randomness complexity, as this like log t of this will just be O of m, which is what we want. But the sample complexity is terrible because recall that we think of delta as exponentially small, so this is exponentially many samples. So natural idea is, can we try higher wise independence? But like if you want to generate L wise independent sequence, you need to pay at least L times m random bits. Just by looking at the first L samples, it's uniformly random, so it costs you L times m random bits. So if we just want to use O of m random bits, we can just use constant L here. Otherwise, we just exceed the budget we have. And researchers have made a lot of constructions that come up with a lot of very smart techniques. And I want to highlight that Zuckerman in 1994 or 1997 showed that extractors are basically equivalent to samplers. So using a construction of extractors, he showed that we can just use 1 plus alpha times the optimal randomness complexity, where alpha is an arbitrarily small positive constant. And the sample complexity is slightly worse, but it's like still poly m. And using the famous zigzag construction, we have the best sampler we have so far, which just using which has almost optimal randomness complexity, and for the sample complexity is poly opt, which is like poly 1 over epsilon squared times log 1 over delta. And we should know that if you care about a good like what we care in this work, a very good sample complexity, we can use expanded random walks. But the randomness complexity is like not so good because recall that in expanded random walks, when you walk to the next node, you need a fresh random bit. So it costs you m plus the number of samples, so which is not good. So it's like m plus poly m, not just O of m. In this work, we get a asymptotically optimal randomness complexity. And for the sample randomness complexity, and for the sample complexity, we get up to the 1 plus alpha. So it's like we get near optimal in both worlds. And this leads to a simple application, which is that, like as we said, samplers imply extractors. So for extractor with epsilon error on the NK source, the optimal seed length will be log n minus k plus 2 log 1 over epsilon. And although we have a lot of great constructions that the famous GUV construction that gives us asymptotically optimal seed length, but if we really care about the constant in this big O, we do not know many constructions. Like leftover hash lemma gives us a nice constant 2 on the log 1 over epsilon, but for the log n is not good. And expanded random walks gives us a perfect seed length, but it requires a very high k, the main entropy. So it requires 1 minus epsilon squared times n, essentially. Epsilon squared times n, essentially. So again, using our using the connection between samplers and extractors, our sampler gives a 2.01 constant in the seed length, and it requires linear main entropy. So it's slightly worse than the expander walks, but it has a much more relaxed constraint on the main entropy. And it's we can also extend the notion of averaging samplers to matrix samplers, because matrices themselves have very good concentration. So imagine that we have a set of matrices, and for each one of them, it has bounded norm. And by just drawing 1 over epsilon squared times log d over delta independent samples, you took the average over these matrices, and it's still very close to the expectation of this whole set in the sense of the spectral norm. So this is called matrix transfer bound. It's non-trivial because by just taking the entry-wise concentration analysis, you cannot get such a good bound. The d actually the dimension d would not be in the log; it would be outside of the log. And so we can also try to de-randomize this process where we call it, it is called matrix samplers, where you still output the samples from this 2 to the m spaces. You're not like outputting matrices, but the way you evaluate your sampler would be like you want to fool all the functions on this of the matrix values. And the interesting choice would be like d equals exponential of theta m, because this will give us a poly m. So you should think of this d as exponentially big. And for matrix samplers, there are a lot of things to do. Non-explicitly, the best you can hope for is m plus 2 times log d over delta. And the sample complexity, the opt d here will be 1 over epsilon squared times log d over delta. And what we did, we achieved this randomness complexity to be m plus o of log 1 over delta plus log d over epsilon times log d. So basically, we have an extra log d in this randomness complexity. So it's like we achieve all of a total of the optimal randomness complexity. And again, if you think of this d as exponentially large, as like exponential to m, so we basically achieve m log m. Yep. So for the sample complexity, still we get opt to the 1 plus alpha for this matrix case. Yeah. So what techniques did we use in those constructions? And it starts from a very simple idea, which was first observed by Gojek, is that subsampling from samples still yields a sampler. So what does that mean? That means that, so what does a sampler does? So there's a whole space of 2 to the m points, and the sampler takes some random bits and it generates, say, like T1 samples here from this 2 to the m space. But if you look at those T1 samples, it is itself a nice domain to work on. And you use another sampler to sample from this space, and it yields you some like y1, y2 to yt2 here, and each sample is in the space of domain of T1. You can still do that. And for the next time you pay n to random bits, and you can compose these two samplers and get a sampler of, it's like you don't sample all these red points, you just sample the circle points. And this costs you n1 plus n2 random bits to generate just those T2 samples. So so it's like after you sample some points, you don't query them immediately. You just choose some points from them to query. And it is easy to see that this is still a good sampler, because if you imagine the samp out and samp in be two delta epsilon samplers, you can do a natural union bound plus triangle inequality. And if you treat this f prime being the function that is f prime defined on this T1 domain, and you can see the first term gives you epsilon error with 1 minus delta probability. The second term gives you epsilon error with 1 minus delta probability. It's standard analysis that shows that the sampler gives you a 2 delta 2 epsilon averaging sampler. So this is actually very nice, because if you look at what we did, it's we have two samplers, and actually you can see that for the final sampler, T1 doesn't show up in the final bound. So you can allow T1 to be relatively large. And for the, when we choose this samp out, we just need the sample complexity to be not that terrible, but we need it to surely have a very nice randomness complexity. For the sampling, although this N2 show up in the final bound, it's this sampling only works on a small domain. It works on T1, not this 2 to the m large domain. So in the outer sampler, it already like makes this domain size exponentially small, so it can have a bad dependence on this randomness complexity. But we surely want the sample complexity to be good, because the final sample complexity would just be T2 itself. And so this allows us to try different samplers with different advantages here. And like, for example, for the sampling, you cannot use the matrix random walks, although it has not terrible randomness complexity and good sample complexity, because the expanded random walks has actually good dependence on the domain size, but it has an epsilon in the bound, so which doesn't help, which a small domain doesn't help you. So what do we choose for the sample out? We naturally use the extractor-based RVW sampler, which gives you essentially optimal randomness complexity and polyopt sample complexity. For the inner sampler, now the inner sampler works on the domain of the of T1, so which is 2 to the O of log 1 over epsilon plus log 1 over delta. And we just want to pay log 1 over delta random bits here. So the question is, how good can the sample complexity get? Now, but for small domains, we actually it will be very nice to work on the small domain, because recall that for the first example we gave, like when you choose the pairwise independent samples, you cannot choose a very large L for L-wise independent samples because you need to pay L times M random bits. But now the M gets pretty small now. So it allows you to choose a very large L here. And so if we want to pay log 1 over delta random bits, we can generate log 1 over delta over log 1 over epsilon plus log 1 over delta wise independent sequence. And this gives you a lot of saves. And follow this idea, we use almost L-wise independent sequence and get a very nice small domain sampler, which costs O of log 1 over delta random bits and gives you opt to the 1 plus alpha samples. Yeah. And by composing the outer sampler, which is basically an extractor, and for the inner sampler, which is almost L-wise independent sequence, our final sampler just looks pretty clean, and it gives you a very good bound. And actually, it would be nice, very interesting to look at this through a PRG view. So basically, a sampler can be seen as a PRG that's filling the testing function of epsilon close to expectation, because you want it to perform the same as uniform random bits, uniform random samples. So basically, you want to fool it with delta error, but the testing function is the epsilon close. And the final sampler looks like this, and this has the same structure as the Nissan-Zuckerman generator. But if you just apply the Nissan-Zuckerman generator, the analysis here, you will get a bad bound, because recall that for NZ, you essentially need the extractor error to be pretty small, because once you make an error in the, like, say, a branching program, you have no control over like what happens next. So essentially, you want a union bound over every step. But for a sampler here, you can, like, those errors just cancel out naturally, right? You just like you took the average over the errors, not just a sum of the errors. So this allows you to have a very large error extractor, and you can have a good bound here, just for the analysis on the sampling problem, not a general branching program. Okay, so these techniques are very simple here, so it can easily be generalized. So what we did in the real valued function case, we first choose an outer sampler with good randomness complexity, and we use the composition scheme to reduce the problem to the small domain sampling, and then we just design a sampler for small domains. And all of these things can be generalized to matrix case. Although, like, there are some difficulties, like there's no known good matrix sampler as the RVW construction. So we start from a much higher sample complexity. We start from just a naive union bound over entries thing. And because the starting sample complexity is large, we cannot just do a simple composition, but we can iteratively do this thing to, like, before it was like polynomially reduce the size. Now it's like exponentially reduce the size. But sure, you need, if you want to do this exponentially, reduce the sample complexity, you need to iterate this for log n times. So this results in the O tilde in the final randomness complexity bound instead of just the optimal thing. And for the sampler for small domains, we can just do all the analysis on the concentration of, it used to be like random values, now it's random matrices, and it just follows and gets a very good sampler for small domains. And there, to get the final bound we got, you need to do the extra step and shows that basically an epsilon matrix sampler will be enough to imply a good delta epsilon matrix sampler given a good delta epsilon scalar valued averaging sampler. So this saves you from, when you get a bound that has not so great dependence on delta, you can replace it by epsilon. So to summarize, we give an averaging sampler with n plus O of log 1 over delta randomness complexity, but and sample complexity of opt to the 1 plus alpha. For the matrix sampler, we didn't get the optimal randomness complexity, and we have an extra logarithmic loss here. And for the sample complexity, still we get up to the 1 plus alpha. And this leaves a few open directions. First, like the natural thing is to remove the 1 plus alpha, remove the alpha here. We want to get of opt sample complexity. And for the matrix sampler problem, we want to get the asymptotically optimal randomness complexity and as the most important thing to do. And another problem is that when you think of this matrix sampling, it just works for a specific normed vector space, which is on the domain of d by d matrices, and you measure it through the spectral norm. And can we extend the result to other normed vector space and still has this very good de-randomization thing? Okay, thank you. Yep. So it's like 1 over alpha here. Yeah.
You're talking about extending your results to other non-vector space. Do you have any candidates?
That's a very nice question. I'm actually not sure what is the most interesting norm-vector space to work on. Like for Frobenius norm, I believe the best thing you can do is just union bound over entries, because that's what Frobenius norm try to bound. And a nice norm-vector space to work on will have some non-trivial concentration on itself, just like the spectral norms. So I think I'm not sure which is the best thing to work on, and it must have some nice concentration there. Yeah.
Then you can also look at some family of matrices.
Yeah, sure. Yeah, you can just look at. Yeah. Thank you.